Hello everyone, welcome back to Fluid Mechanics 2. In this model, we're going to talk about viscous flow in pipe or duct. And in other course, you maybe find that it is also similar with the topic what we call internal flow. So let's go without further ado. Let's go directly to our material. Let's talk about internal flow. What we will learn about internal flow. Uh, what we are going to discuss in this course. The first one it is the behavior of fluids flowing inside pipes and duct. I think you are familiar with pipe, but actually it is different compared to the duct. What is the difference between pipe and the duct? Actually, it is just about the shape and the design of the cross sectional of these two things. So for pipes, it's normally uh, the cross sectional view. It is like it is will be cylindrical. You can see here. Sorry, you can see here it is a pipe. But when we talk about the duct, so the cross sectional view of it, it is can be rectangular or sometimes maybe oval or round. So this is the most important thing about the difference between pipe and duct. And then the thing that we will discuss in this course, it is about the difference between laminar, transitional, and turbulent flow regimes. We'll discuss about it later. And then we will also discuss about how to determine pressure losses, friction factor, and head losses, especially in terms of the piping system. And then we're gonna learn about analysis of major and minor losses in pipe system. And the last, of course, we're gonna talk about applications of continuity, energy, and momentum equations to internal flows, like what we have discussed in the previous sections or in the previous models. So these three things or these three equations will be with us in a couple, I think in the next of material of fluid mechanics too. So that's why if you are not familiar, or if you are not understanding about continuity, energy, and momentum equations, you can go back to the previous material or previous model, especially the first model of this course. So that's all the thing that we will discuss or we will learn in these models, and I hope you stay focused with the course because it is really important for us as mechanical engineer. Why it is important for mechanical engineers? First, I think it is because fundamental to engineering designs. At almost case or systems, if you talk about engineering, from power plants, HVAC, or heat ventilations and air conditioning, turbines, whether it is hydro turbine or wind turbine or gas turbine, and also hydraulic system, everything, all of this involve internal fluid flow. So that's why this is very important for us. You can see from the picture, this is uh, how we use piping system in a building when we need to have when we need to design the HVAC or the system of this building. And also in here you can see that it is very useful and it is very fundamental in Flens. So understanding piping or internal flow will be very beneficial for us. And then the second one, the second reasons why it is important for us is because when we talk about energy efficiency, so understanding pipe flow helps minimize losses and optimize system performance. Of course, we will learn about the losses in here. So if we understand about it, our system will be more efficient and more effective. And then the third reason, because of practical relevance. So understanding piping networks, cooling system, and fluid transfer system will be something that will be very important for you in terms of designing the power plant, building, another thing. And the last one, it is the foundation for advanced topic such as turbo machinery, heat exchanger, and computational fluid dynamics. For example, in heat exchanger, if you are familiar with heat pipe, for example, so understanding the fluid flow phenomena inside this small pipe will increase your ability to design the heat pipe, especially to improve uh, the ability of this heat pipe to transfer the heat. Uh, we can talk about the coefficient of heat transfer. Also, computational fluid dynamics, understanding internal flow will help us to understand about how to use computational fluid dynamics. So let's talk about classifications of internal flow. So we can classify the internal flow into three categories. The first one based on flow regimes. So based on this category, we will have a laminar flow, which is a smooth and orderly fluid motions. The layers slide past each other, which is normally uniform. And the second one, it is transitional flow. It is between laminar and turbulence, unstable and fluctuating, but not as much as turbulent flow. And the last one, turbulent flow, is chaotic motions with eddies and mixing across the pipe. The second classifications of internal flow it is based on driving force. The first one, force flow caused by pumps or fans. It is common in engineering system. And the second one is about natural flow driven by buoyancy or density difference. So like gravity force, if you have for example, in hydroturbine, system, you need to flow the water from the dam into the turbine. We don't need to use pumps or other thing because normally the dam is upside of the turbine. So with the gravitational force, uh, the the water will flow into the turbine, of course, with a piping system. And the last classifications, it is based on flow development. So especially if we talk about pipe flow, we're going to talk about these two kinds of flow developments. The first one, developing flow, where velocity profile is changing along the pipe. We call it also as entrance regions. And the second one, it is fully developed flow, where velocity profile remains constant along the length of the pipe. So there are three classifications of internal flow. Maybe In some references, you'll find other classifications, but it is the most common classifications that you need to understand about internal flow.